Hello everyone. We are the Turbomachinery and Heat Transfer Research Group of Technion IIT, and what you see here is our proposed concept of additively manufactured preassembled turbojet engines for UAVs. The effort aims to address the disproportionately high cost and limited availability of commonly used microturbojet engines. Instead of relying on conventional manufacturing techniques and assembly processes, additive manufacturing of metals can revolutionize the market of limited lifetime engines. The enabling technology is system-level design optimization of self-supporting layouts towards additive manufacturing. Thermodynamics, stress analysis, and heat transfer are coupled in a specially developed multi-physics framework which also accounts for limitations of self-supported additive manufacturing of monolithic turbomachinery, hydrostatic bearings, and porous media combustors. This approach then enables to expand the microjet engine's design space via previously unexplored methodologies. Our solution concept relies on simultaneous uninterrupted print of preassembled rotating and stationary parts. This approach leads to a unique disposable microturbojet engine design, which has only two parts. A monolithic rotor which encompasses the turbine, the hydrostatic bearing journal, and the compressor. And a stationary section which is comprised of the heat exchanger, the nozzle guide vanes, the combustor, the diffuser, the intake, and the bearing housing. The effort leverages our existing knowledge while applying it to direct metal laser sintering of Inconel. Self-supported additive manufacturing and hydrostatic bearings were previously demonstrated in a small-scale pre-assembled rotorstator turbomachinery system manufactured from plastic. Premixed porous media combustor and 3D printed monolithic Inconel rotors were also produced and tested in relevant conditions. Overall, single-step fabrication of self-supported architectures will enable platform producers to directly manufacture the engines on demand, while diminishing their cost to equipment depreciation and price of raw material. What you see here is a small-scale turbine-driven compressor manufactured from PETG plastic directly in its pre-assembled form via a single 3D printing process. At first, you can see the rotor floating on air-driven hydrostatic bearing. Then, when the turbine is powered by a pressurized air supply, the rotor accelerates to its nominal speed of 36,000 RPM. In this image, you can see the internal structure of the turbo machine, with the hydrostatic bearing denoted by the red rectangle. Now, you can see the time-lapse video of the additive manufacturing process for engine representative geometry, which includes both the rotor and the stator in a single 3D printing process. And finally, you can see the outcomes of the print, which produces easily detachable components and showcases the inner structure of the engine concept.